Good morning, Ms. Asfa. Are you able to hear me?
Yeah, am I audible?
Yeah, you are audible. Thank you.
Should I share my screen now?
I think yes, you can go ahead.
Share screen. Where is the option?
There's a small next to your cancel button, end button.
Yeah.
Presenting.
Virtual background? No. Change layout preferences, enter full screen. Picture in picture. Okay. Change layout. No, it doesn't show share your screen option.
No, near the mic.
There is one
Near
small.
the mic, the second one, right? Not near
Yeah.
the stop. Yeah. Share screen is there.
Yeah.
I'm going to share my screen. Please let me know if I can. If you can see what I share.
Can you just switch
Yeah.
on your video, ma'am?
Switch on my video also.
Yeah.
Launch.
Yeah, is it visible?
No. Yes.
Yes.
Yeah, this is fine. Yeah.
Can you make your presentation full screen?
And we cannot see.
No, I think some internet issues are there.
Yeah. Is the presentation visible?
Presentation is visible, but your video is not visible, ma'am. Can you just again see the settings, video settings? Take the video.
I'll just check. Okay, I can see myself because my video is on.
Okay.
Yeah, I can see.
So anyway, during the presentation, my video may not be on. Is that okay?
It should be okay.
Yeah, that's fine.
That is fine, right? So for the time being, stop
So
sharing.
we are able to see Gomati.
Now you're able to
Ma'am's
see?
video also we are able to see. Prashanti here.
Okay, fine. Start introducing.
So I've tested share screen after the first part. Maybe perhaps you'll be introducing. After that, I will share my screen.
Yeah,
Alright?
sure. Okay. Thank you, ma'am. Just waiting for just few more participants to join.
Right.
And
Okay.
please start the session.
So I'm talking to Gomati, madam?
Yes.
Yes. Okay. Which department, ma'am?
Pardon?
Department of?
No, I'm a program coordinator for IIT Tirupati Navavishkar Hub Foundation.
Okay. All right. Okay.
Thank you.
So this is being organized by which department? Some department of
No,
IIT
it's not
Tirupati?
a department. It's a separate Section 8 company. It's a technology innovation hub.
All right. Fine. Satyabama Institute of Science and Technology, right?
No. That's a separate institute. So we are based at IIT Tirupati. We are a separate Section 8 company under IIT Tirupati, and we are doing this program in collaboration with Satyabama Institute.
Okay. Fine. Got it.
Yeah.
So yes, I asked that question. Whom are we? The target audience today would be students or anyone from across?
We have even faculties and research scholars.
Faculties and research scholars. Okay, all right.
Thank you.
Let me know when to begin, okay?
I'll just introduce you and then you can start the presentation.
Yeah, sure.
Just waiting, like there are only 13 attendees, just for waiting for another few more to join, and then we immediately will start the session.
No problem, absolutely, no problem. Okay.
Okay. A very good morning to everyone present here. Yeah, I request everyone to mute their speakers and mic. We're going to start the session. I request all the participants to mute their mic. I take this opportunity to welcome all of you for the second day workshop on hyperspectral remote sensing and its applications. I think the first day we had three beautiful sessions by our key speakers. Now, so today we will be having 4 more sessions, starting with our key speaker for today, Ms. Asfa Siddiqui. So before I could start the session, I just wanted to share this quote with all of you. Color is a color is a power which directly influences the soul, and hyperspectral is one which captures these colors of the mother nature. So with that note, I would like to start this beautiful day and this beautiful workshop. Welcome everyone. As a part of TIH, are very happy to have you all here for our second day international online workshop on hyperspectral remote sensing and its applications. I take this opportunity to welcome our key speaker of the day, Ms. Asfa Siddiqui. Ms. Asfa Siddiqui is currently working as a scientist at Indian Institute of Remote Sensing, Indian Space Research Organization since 2014. She did her bachelor's in architecture from Government College of Architecture, Lucknow in 2011, and master's in planning with specialization in urban planning from School of Planning and Architecture, New Delhi. She worked at NIT Kozhikode, Calicut prior to joining ISRO. She is a double gold medalist and have received government scholarship and awards at college level. She has more than 45 scholarships and awards. She has more than 45 publications in journals, conferences, and book chapters to her credit. Her work focus on remote sensing based urban and regional area analysis with emphasis on energy and environment, especially urban heat island effect and urban air pollution. Ma'am, we are very happy to have you here today. we hope for the next 1 hour you will have a great time, and all our participants will be very happy and will be gained with so much of knowledge on urban studies from you. Thank you, ma'am. I request you to preside the session now.
Sure. Thank you for the modest introduction. I am very pleased to have taking this lecture today. So I'm sharing my screen as of now, right?
Yeah.
Yeah. So is my presentation visible?
Yes, ma'am. It's visible.
Yes. So today we are going to talk about hyperspectral remote sensing for urban areas. Now we all know and we have all seen that in first day's session you are acquainted with the sensors, with the introduction of what hyperspectral data looks like and how it is so useful for characterization of materials on the ground. It can be related to forest or agriculture or urban areas or maybe geology. So it has various applications. Today we are going to delve into a little detail about how an unexplored field of urban areas can also be sensed using hyperspectral remote sensing. However, not much work has been done in this regard, at least in India for sure, I can say that. All right, so yeah. I'm so sorry. Yes. So why is there a need? Because urban areas are characteristic of natural as well as man-made features, man-made targets. So it becomes an ensemble of both the elements on Earth, and hence it becomes a little difficult also to map urban areas. You need to understand the natural as well as the anthropogenic targets that are available on the ground, and per se we are going to map all the urban features present on in an urban purview. So it is important to understand that hyperspectral remote sensing for urban areas, we are going to delve in the electromagnetic spectrum over a range of that we have spectroradiometers up till 400 or 350 to 2500 nanometer. It is specifically 0.35 micrometer to 2.5 micrometer. So not much of the higher wavelengths have been explored using spectroradiometers per se. Hyperspectral remote sensing for urban areas specifically, you need most of the information that is embedded in the shortwave infrared band and the TIR band. But that doesn't mean that the optical wavelength region or the visible in NIR region cannot be used for urban area analysis. So we should understand that how it can be done, how quantitative and qualitative analysis can be done using hyperspectral data, and which bands particularly would be helpful. Additionally, how we are going to analyze urban areas by maybe spectrally enhancing the spectra, or maybe some fusion techniques that can help us analyze the data better. We have had certain studies across the world, and primarily once the World Trade Center collapsed, hyperspectral remote sensing was used for understanding the dust that had accumulated into the surrounding areas. So they wanted to see that how the World Trade Center's collapse has affected the nearby regions and where the debris has fallen. So for that, hyperspectral for the first time was used. However, it has been used for differentiating paving materials also. So the three-dimensional urban structure by fusion technique of LiDAR data and hyperspectral data has also been used. And the age of the buildings or the age of the roads have also been characterized using hyperspectral data. So where all it can be used. So in the nutshell, it can be used for very basic urban land use land cover mapping, maybe up to, we know that urban land use can be classified from level 1 to level 4. However, hyperspectral deals with an additional area, maybe more detailed, that is level 5 and level 6 kind of classification also, where the materials and within the materials, the sub-materials can also be classified. So enhanced urban land use land cover mapping in terms of materials can be done using hyperspectral data. Roof type composition, road type composition, and the condition mapping can also be done using hyperspectral data, depending upon the dust accumulated, the cracks within the roads that can also be mapped, and the roof condition can also be Urban tree monitoring can be done. It is extensively used for vegetation mapping, hyperspectral data, and forest species mapping. And the same can be done using hyperspectral for urban areas where we need to analyze which kind of trees are available in the urban purview. Also, I would like to mention here that there was a drive once when eucalyptus trees were being removed from inside the urban periphery. Why? Because eucalyptus trees absorb a lot of moisture and the water table was being affected because of it. So that kind of analysis where people were identifying eucalyptus trees from the cities, that could have been reduced using remote sensing and using this hyperspectral data, HSRS data. Urban heat island effect can also be monitored and it can be correlated with materials. So we have studies, our own studies, where I will show you that how we have tried to correlate land surface temperature with material dynamics. Flash flood monitoring can be done. You can always understand not only microwave data, but hyperspectral data, and a combination of both can also be used for flash flood monitoring. Then you can always have garbage sites, solid waste management sites, detecting oil contaminated soils. Additionally, you can fuse data for better analysis of the urban areas. So all these applications can be can be done. So what are the challenges with urban areas? This is pertinent to mention at this point of time because since in the initial slide I had told you that not much papers or not much of analysis you will see, especially in context of urban areas where hyperspectral has been used. So what is so challenging that people do not delve into analyzing urban areas using hyperspectral data? So one of the most important problem is that the urban areas are to changes with time. So there is dust, there is smoke that alters the outer surrounding of the urban materials, and the rooftops or the road tops, they are all altered with time. So they are modified. So these modified procedures have to be analyzed from time to time, and that is a tedious process. So this is one of the challenge. Then there is not always a very characteristic absorption feature, because what are the materials made up of? They are going to have a characteristic feature of maybe iron oxide or maybe some calcium deposits, or so these kind of features cannot along with other materials when they combine together do not show characteristic absorption curves. So this is one problem that we are going to face with urban areas. Then, as I have told you, they alter the coatings, algae, dust, everything changes the context. Then mixed spectral signatures are found if the spatial resolution is not very nice, or not very enhanced. I would rather speak it that way, that Hyperion data, one that has been used so extensively for mapping of other features, however, cannot be used very extensively for urban areas because it's a 30-meter spatial resolution data, and in 30 meters you will have mixed targets, mixed spectral signatures, very difficult to map urban areas. So with 30 meters might as well use optical data or not the hyperspectral data. But when you really want to go ahead with material characterization, you might need the high resolution hyperspectral data, and that is how we used a lot of Everest data, and there was a collaborative mission with Everest that was known as Everest NG. It was an ISRO-JAXA collaborative mission, and that data was used, which varied from 3 to 10 meters spatial resolution that was used. Then in India also by regions, as you know, the vernacular architecture is available. Same way, the material dynamics of the vernacular architecture changes. So locally available materials are used. It is highly susceptible to regionality, and you need to have a inventory, or you need to have the database of all the spectral signatures of the natural and the man-made materials in India. We do not have, we lack that. So that is also one problem that we might face when we are working with urban areas. Reflectance throughout the day changes, so that is why we generally want to match the spectroradiometer readings only across the days where the shadow effect is minimal. So these are some of the reasons why we do not study so much of urban areas. But having said that, we at IIRS have studied remote sensing based urban material characterization especially using hyperspectral data. So just to quickly show you the spectral signatures of the roof types, you can see that we have mapped using spectroradiometer readings at Ahmedabad. That was our first field in 2016, where we have specially understood the rooftop materials, be it asbestos, PVC, tin, china mosaic, marble, plastic fiber, polythene, and stone. So you can see that the characteristic dip can only be seen in marble, and most of the features show us that there is a lesser reflectance pattern in the initial 1.5 micrometer, and after 1.5 micrometer there is a gradual increase towards higher wavelengths. Then these are the road types: tar, bitumen, concrete, stone. So we can see that there is no characteristic dip in these features, but having said that, I will tell you that where concrete, how a freshly laid concrete will look like, how our road would look like. So all these details I'm going to share with you. Also water, soil and grass, because natural features were also as equally important. So we are going to delve into understanding those also. So let us start with vegetation, because vegetation is the premise, and I've always told in all my lectures, if you go ahead and see any of my lectures online, YouTube or anything, you would come to know that I always say that you should always have a remote sensing data set that shows you contrast between urban areas and vegetation. So you should use a full bloom data. Full bloom data means a data in which the vegetation is at its peak. The non-urban areas, or characteristically the rural areas, have most of the vegetation pattern prevalent at that time. It is not cut. It doesn't behave like a barren area. So for that, you need to have such date imagery depending upon the region that you are focusing on, because that gives contrast and it helps you to understand the or extract the urban areas better. So vegetation, what does a vegetation peak suggest, and what are the characteristic features? So reflectance peak, as you can see the spectral profile of vegetation, you can see that the reflectance peak is in the green region because of the chlorophyll absorptions at 450, 680 nanometers. And mostly the water content absorptions, or the water absorption profiles, you can see at relatively 980, means 0.98, 1.2, 1.4, 1.9, mostly because of H2O absorptions, and lignocellulose absorptions are available at 2.1 and 2.3 nanometers. So this is the characteristic of the vegetation profile. And once you see that in the NIR region also there is a higher reflectance, however in the in the green region, the reflectance pattern is specifically higher. In the bare soil, mostly the bare soil and will have clay mineral absorption, typically targeted at 2.2 micrometers. And if the bare soil is showing some the vegetation is showing the similar signature as bare soil, then you may say that it is a non-photosynthetic vegetation, or the NPV, in which it behaves like a bare soil characteristic, in which you will see that the clay mineral absorption, if it is available, then only it is a bare soil. And if that clay mineral absorption is not available at roughly around 2 to 2.2 micrometer, then you can say that this is a non-photosynthetic vegetation. So the difference between the two can only be understood by this clay mineral absorption feature. So what are we actually talking about in these spectral signatures? The moment I say that my signature is different from somebody else's signature, or some of your signature, we are actually signing and making it as our signature. So when our signatures are different, we will have some way of writing A, or maybe some dots, or maybe some lines. So that is how our signatures are different. Similarly, all the materials present on the ground have different spectral signatures present, or spectral peaks and spectral absorptions. And the peaks are characterized by reflectance. Now, as we know, the reflectance is either from 0 to 1 or 0 to 100, depending upon the scale factor. So 100% reflectance means it is a white object, or maybe a reflecting object, which is typically a light colored object. So what are those objects? Maybe a roof which is painted with white color. It may have reflectance that is absolutely 100%. Again, depending upon the material of the object. So here we are talking not only about the outer appearance, we are also talking about the signature or the material that it is composed of. Then you can see the built up surfaces in the form of roof tiles. So what are they made up of? It can be wood shingle roof. So wood shingle roof will always show you the signature of the typical lignocellulose. I told you lignocellulose at 2.1, 2.2, 2.3 micrometer. Then it can be a concrete roof. A concrete roof will not show any characteristic dip or any characteristic reflectance profile per se, but it will have a consistent reflectance profile. Then you can have a red tile roof. If red tile roof is available, then you will always see that the amount of Fe is or the iron oxide characteristic dip is available. Similarly, in asphalt, the asphalt or the freshly laid asphalt will always have a low spectral profile, so a low spectral reflectance, no characteristic dip as per se. So let us delve into understanding what are the spectral properties of the roof. So reflectance increases in the NIR in the sphere region. As I told you that the wood shingles will always have a lignocellulose absorption in the sphere region. If it is a burnt tile or the red tile, then it will always have iron oxide absorptions, typically at 0.5, 2.6, 0.67, maybe 0.8, 0.9 micrometers, and it will be losing out on water. So the loss of water due to the firing process will always be visible. Similarly, concrete is made up of cement, gravel, water, and other ingredients. So specific absorptions of due to calcium carbonate would be available at 2.3, and calcite, as I told you, would be available approximately at 0.24 micrometers. The calcite and dolomite absorptions. Similarly, if you see the content of clay in concrete, so you will have a characteristic absorption feature at 0.217 micrometer. But again, having said that, many a times spatial resolution also has a role to play in this. You may not be able to see these characteristic dips and characteristic absorption features. I would skip on swimming pools. So asphalt on the freshly laid asphalt and the old asphalt and concrete, the freshly laid concrete and the old concrete will have only one major difference. The asphalt will have low reflectance and the increase in the reflectance across around 2100 nanometers. However, in concrete, you will see that the freshly laid concrete will have high reflectance initially, and the old concrete will, due to material aging, due to dust accumulation, and due to the calcium carbonate absorptions and decrease of reflectance may be observed in the old concrete. So you can see that the deterioration in asphalt will lead to high reflectance. However, in concrete, it will lead to lower or the decrease in reflectance. So this is the primary difference between the two. And once you plot the spectral signatures, you'll be able to see on the right. I might as well you see that in the asphalt, the reflectance patterns are very, very low, approximately 0 to 5 you can see. However, in concrete, the reflectance is a little higher. So this is the general understanding of concrete. No spectral absorption feature you'll be able to see except for 0.235 micrometer. That is the calcium absorptions. So yes, yes. So how do you spectrally separate the absorption features or the different materials from each other? So there's a formula that is used very, very commonly, that is known as Bhattacharya distance, and this distance is basically a separability score that tells you the difference between two spectral signatures. They might be same, but there may be some spectral absorption features that are present, and they may be different. So by using Bhattacharya distance, there are studies. It was a very good study by Herald in 2004, where he has tried to understand this different spectral peaks and different spectral absorptions of different features. You can see we generally do not have wood shingle roofs in our these climatic zones that we live in, composite climates. But yes, in hilly areas you may have the wood shingle roofs as well. So what his understanding of the scores, it emphasized that spectral the scores suggest that green vegetation, gravel roads, and red tile roofs are extremely distinct from each other. That means the scores are very higher. However, very low scores can be available in concrete roof surfaces and parking lots because they are made up of the same kind of material and the bare soil as well. So they are made up of same kind of material. So there's low separability. So these kind of mathematical indice-based understanding can also be made for distinction between different materials. I want to come to my case studies as quickly as possible so that you can understand that how we have translated the literature that we have read till now into the work that we have done. Then, yeah, okay. So, okay, this is a small study. Okay, I'll tell you that we have used a fusion of LIDAR data with hyperspectral data. So we were new to this field way back, and we wanted to explore that how hyperspectral data can be used for material characterization, and we also wanted to use some other classification technique apart from the ones that we generally use, for example the pixel based classification, or maybe the spectral angle mapper or support vector machine. So we used a third dimension LIDAR data because many a times we have seen through Bhattacharya distance that parking lots may have a similarity with bare soil. Or what can be a difference, or what can be a difference for differentiation of these two materials? So there can be a concrete rooftop also, and there can be a concrete road also. So how do we distinguish between these two materials? So LIDAR technology, or the three-dimensional technology in the form of LIDAR. I hope you know what LIDAR is. It is light detection and ranging. It is a point cloud data basically, and it helps you in understanding the height perception of any urban materials, and it can be helpful in providing you DEMs, or digital elevation models. And when we are working with urban areas, we call that digital elevation model as digital surface model. So that digital surface model can be fused or can be used in conjunction with hyperspectral data for extracting information. Here we have used one more thing that is known as, what do I say? One thing that is fusion technique and rule-based classification. So in rule-based classification for San Diego, California, we have used SAM classification and seen the classification accuracy. SAM is spectral angle mapper. It tells you the relation between the target and the actual spectral signature, and it tells you the angle of difference. If the angle is lesser, there is more similarity. If the angle is more, then there is lesser similarity. So spectral angle mappers classification for different materials did not give us the desired accuracy that we were looking for. And we went ahead with knowledge-based classification using some rules. So what are those rules? We used NDVI, and the height that was derived from the LIDAR data. So I don't know how many of you know what NDVI and NDBI is. So NDVI is a metric for understanding the vegetation profile, and NDBI is a metric for understanding where built-up areas are present. So we use that in DICE, and we also use the height data that we got from LIDAR. And NDSM means normalized differential surface model. So digital surface model, I'm so sorry. What do you mean by NDSM? So okay, can I ask questions in the middle if anyone can answer? Do you know what a digital elevation model is, and what is the difference between digital elevation model and digital surface model? Anyone? Okay. Okay, so since I have not received any answer, I assume that maybe all of you are knowing, or maybe none of you. Normalized difference vegetation index, normalized difference bareness index. I hope.
This is Prashanti. Sorry to disturb. We have attendee Yash who has raised his hand.
Okay. I'm unable to see the hand actually. Can you just let me know what do you?
You want, can we enable Yash to talk?
Okay, so we have not enabled that. All right, it's okay. We can talk that during discussion. I'll tell what it means. Actually, digital elevation model is a generic term. So it is a 100-meter spatial resolution DEM. It can be a 30 meters DEM. But the moment digital elevation model is divided into two parts, it is digital terrain model and digital surface model. So terrain model will not have any buildings or trees across it. It is only a bare terrain model. However, surface model tells you about the building areas also, the vegetation profile also, the heights of that. And NDSM, that means the moment you remove the terrain from the surface model, it is a normalized DSM. Only the buildings and the building heights will be available to you. So that was used for our understanding of knowledge-based classification. So we saw that using some of these decision trees for knowledge-based classification, we could improve the accuracy to something around 85 or maybe more. So this is a comparison between SAM, that is a spectral angle mapper, and knowledge-based classification. So in the first image, you have the actual imagery, the Everest 5.8 meters. In the second image, you have the SAM classification, and at special locations 1, 2, 3, you can see how there is misclassification. However, in the rule-based or the knowledge-based classification, you can see that how the classification accuracies have improved. Also, we have certain pixels that are not into any category. So this is how we have improved the classification accuracy. We have also tried to extract the roads using knowledge-based classification in an efficient way. Overclassification was observed using SAM classification. So we concluded that LIDAR and knowledge-based classification has improved the classification accuracy. You can also try it while you are working on any of your study area. So we also tried to employ spectral similarity approach for urban material library building, because we went on the ground to collect the data. So for that, we first tried to understand all the profiles of the materials that are available on the ground, be it water, soil, vegetation, concrete, or asphalt. And then we used spectral similarity approach called SAM and Euclidean distance measure, city block distance measure, for understanding that how the spectral profiles are changing. So using a conventional, so you can plot all the spectral profiles. So supposedly on ground, when you go and you take 20 spectral profiles or 30 spectral profiles of the same material, then there are certain spectral profiles that do not fit, or they are the misfit or the impure profiles. So for that, one way is conventional rejection of the spectral profile, and the second is using spectral similarity approach, how you can delete the unwanted spectra. So one of the areas, I think it was Mumbai, we tried to map using the data that was conventionally rejected using the spectral profiles, and in one we used the non-conventional spectral similarity approach profiles, and we could see that the overclassification here was reduced using the non-conventionally used spectral profile. So we can see that how the canals and the roads were distinctly understandable using this kind of data. So the classification accuracy basically enhanced. I'll tell you fusion later because there's a reason why I'll tell you later. This is one of the very important studies that we had done using hyperspectral image super resolution. Now, there are two kinds of super resolutions that can be done. One is single frame super resolution technique, and the other is multiple frame super resolution technique. So what is the difference? When multiple frame super resolution technique is used, then you have approximately 2 to 3 angles of data that is available. However, if you use a single frame super resolution technique, then you use only one data set, and you improve the spatial resolution of data using this kind of technique. So you know that urban areas contain different materials and land cover types from different features. But due to availability of contiguous bands at narrow wavelength, hyperspectral sensors can also help in distinguishing identical feature classes. But highly informative spectral and spatial content is difficult to overcome, especially at the hardware level. So we can use resolution enhancement technique. So one of which is super resolution, and super resolution algorithm helps in the enhancement and retains the spectral characteristics also while visualizing the entire scene at a higher scale. So in this particular exercise that we had done, we had used 4 single frame super resolution techniques, and 3 of which are based on image learning, and 1 is based on reconstruction approach. And this entire thing has been used on Everest NG, the ISRO NASA Everest NG mission. And it was used in near an area of Kankaria, which is located in Ahmedabad. And the spectral profiles of the urban materials and natural features found in the study have been interpreted using optimal sets of bands. And we have also tried to understand the best classification approach using these 4 methods: anchored neighborhood regression, sparse representation, sparse regression in natural prior, and gradient profile prior, using techniques called SAM, which definitely did not provide us with very good results. We have also used support vector machine, and we have also used nearest neighbor object-based image analysis technique. All the 4 techniques were helpful in retaining the spectral profile, and it was also helpful in spatial building of the data. From 8 meters, we had come down to 4 meters. But out of the 4, using some quality metrics, we had tried to analyze which one gave us the best results. So visual and statistical comparison revealed that a sparse regression and natural prior as the best SR process, and anchored neighborhood regression was the worst performing one. And spatial and quality metrics that we had used approximately 8 to 9 indices in total. We also saw that SVM, support vector machine, gave us better accuracy in terms of kappa and overall accuracy in the SRP output. So SRP, as I had told you, sparse regression and natural prior, gave us the best result. And we had tried and correlated that if we would have done normal resampling to the data, then what would have been the result? If we are using some technique of machine learning, for example, single frame super resolution technique, then has the result changed anyway? So yes, we had seen that the nearest neighborhood resampled on the left side. If you can see this image, there was too much of over classification into tin category and in China mosaic category as well. But when you come to the best performing SRP output, then you can see that the over classification has reduced, and this was the worst performing component. But again, the classification accuracy was not so bad here as well. So this was one of the work which we had done. One of the second works that we had done was the characterization of urban materials in Everest NG data using a technique which is known as mixture-tuned matched filtering approach. So what is this mixture-tuned matched filtering approach? Very easily can be done using it is basically a semi-empirical unmixing algorithm, and it can be used for any classification. And the best part of this algorithm is that it is used for reducing the background noise and helps in spectral similarity for abundance of user-defined end members. So you are the one who are defining the user end members, and you are able to distinguish between different materials. So this particular study focused on identifying 6 man-made features and 5 natural features in, again, the city of Ahmedabad, because we had done field there using ISRO NASA airborne campaign of hyperspectral data. And the spatial resolution of this data was roughly around 8 meters. It was actually 8.1 meters. So the dimensionality reduction of the reflectance data was performed using a standard shift difference method of minimum noise fraction. I hope you know what minimum noise fraction technique is. So there is principal component technique and there is minimum noise fraction technique. So these are all data dimensionality reduction techniques. Principal component, however, does not reduce the background noise. However, mixture-tuned match filtering the MNF that is used, that reduces the background noise. So, minimum noise fraction technique, it retains the band possessing the coherent signals and dismisses the noise component within the data. So MNF data was again, it was further exposed to a partial linear spectral unmixing approach of mixture-tuned match filtering, which possesses the character of maximizing the target and member response, and it suppresses the background redundant noise information by a technique which is filtering and then a technique called tuning. So it was observed that this is the entire understanding, and definitely the MNF result is from 0 to 1, where 1 indicates it's a perfect match. It is technically telling you that in each pixel, the proximity of that pixel or the abundance of that pixel belonging to a specific end member target. So you can see that these kind of results were available, and as I told you, that it was observed that the overall accuracy of identification of various materials ranged from approximately 82.3% to something around 87%. And obviously, the higher accuracy was observed in natural materials, but the knowledge materials also helps us in understanding the urban environment, in energy demand and energy balance understanding. So we can see that this is the colored profile, however, this is the black and white profile. We also saw that there was some kind of misclassification between the roads for asphalt and also the river, the Sabarmati river that runs from the city. Just give me a minute. So, yeah. So here we have seen that there is some sort of misclassification. So why we see that misclassification? Because that part of the river was very shallow, and the debris was accumulated below the river, which gave us some this kind of misclassified results. We acknowledge misclassification also because in research, you should understand that not always you get 90% accuracy and 99% accuracy. So somewhere as a researcher, I understand that when we are working by our own hand, we might not be able to get 99% accuracy, and anyone claiming that is a hoax. So you should understand that never be afraid of lesser accuracy, never be afraid of alternate findings, because I have always tried to understand as a researcher that if at all it is not fulfilling the stereotype understanding of a particular phenomena, then what is the reason behind it? So yes, we understood reasons. So that is important for you to also work as a researcher. So I told you that some of the components that we have been working on were asphalt, then concrete, tin, iron, china, mosaic. So look at the analysis here. You can see tin roofs were easily decipherable. Then here you have the marble building that was easily decipherable. Now this is a mosque that is available in the old city area of the city, and you can see that how beautifully marble was characteristically understandable. Then concrete again, there was an ID building and the Sabarmati riverfront, the concrete areas, they were understood, the China mosaic on the buildings, especially in Ahmedabad, a lot of areas China mosaic because it is easy for cleaning and it also helps in for reducing the heat capture component in cities in Ahmedabad where the higher this direct insulation is available. And so these are all published works. Whenever you require to read any of my works, you can always search and you can read. All of these works are published now, so you can have a look. Now, one of this is also a published work. I'll tell you the essence of this work. This was a beautiful work that we had done because of the failure that we observed during MTMF. That yes, the river water was being captured in the asphalt region and there was misclassification. So we needed to rectify it. So what we had done. So in this particular paper, we have tried to assimilate data from two different sensors, hyperspectral. So one technique was that from the entire data within itself, single frame super resolution, enhancing the spatial resolution. One of the alternate could be fusion technique, right? So we used fusion technique on hyperspectral and multispectral data, and we used a technique called fast discrete curvelet transform. So this is a unique fusion technique that is used. You cannot use Brovie technique for this particular classification. It will not give you the requisite results because in fusion, you need to retain not only the spatial profile, but the challenge was to retain the spectral profile also for urban surface material characterization. Obviously. So we used low spatial hyperspectral. So it's not actually low, it's 8 meters, but for understanding purpose, we use low spatial hyperspectral Everest data and high spatial multispectral worldview 3 data. So worldview 3 data of Ahmedabad was used. And 1.24 meter spatial resolution data, multispectral data was available. It was still swill band. We have more number of bands in worldview 3 data. So the resultant high spatial resolution hyperspectral data shows that urban surface material characterization can be done with spatially distinct classes. And how are we doing this process altogether? So the spatial resolution is enhanced by injecting the high frequency details from the high spectral resolution multispectral data in fast discrete curvelet transform, as I told you, is the fusion technique. And then the image fusion based product quality was analyzed using p-comment analysis. Now, what is p-comment? So it's a piecewise convex multiple model end member extraction or detection technique, basically. And we had seen that where the spatial resolutions and the spectral profiles were getting misled or misclassified. Here we have reduced that problem. So look at this image, the figure 3, part A. So here we have the Everest NG data of 8 meter spectral resolution. This one shows the 1.24 meter multispectral data of worldview 3, and here we have the fused data 1 and 2 fused together using FDCT, that is fast discrete curvelet transform. And this is the water end member and the asphalt end member that you can see it -1 sigma and +1 sigma end member extraction. And here if you see that the mixed fraction map, water and asphalt fractional maps, you can see this is the asphalt fractional map and here is the water fractional map. So the misclassification has reduced. Tiles and bare soil also showed some sort of misclassification. So here you can see that the two classifications are totally different. This is again a published paper. You want to know or you want to read more in detail, you can go ahead and read here. Now this is categorically kept work because I wanted to show when I said that urban heating and materials can be classified and categorized together. So I want to tell you that one of my students worked on this work and I had told her to build some relationship between hyperspectral materials and land surface temperature. However, the resolutions were totally different. So it was 8-meter versus 50 meters, but at least it was an attempt. So let us see what we have done here. So the objectives, as says, are to identify the urban materials through classification of hyperspectral, then to compare classification results from SAM and SVM classification techniques, to estimate LST through radiative transfer model that we have done using Landsat data, and to study the relation of urban materials with LST. So here we go. This was the data that was procured using Everest NG mission. This was one band only. We had 3 types like this. So one we had used for this particular work, and you can see that the Everest NG data was at 8.1 meters, the Landsat was 30 meters, and some of the data that we had used was from STAC, the atmospheric data that we had used for radiative transfer algorithm for converting the data into land surface temperature, the thermal band into land surface temperature. So this is the brief methodology that we had used. The hyperspectral data, the accuracy using SVM and SAM, the Landsat data into radiative transfer model based land surface temperature, and the relationship. So look at this. This is the FCC of the study area. This is the SAM classification. However, the classification accuracy was not very high. However, in SVM, we could have a better accuracy, and you can see the different classes, which I showed you on a smaller area near Kankaryale. Here we have the entire scene to our disposal. So you can see that how we have used this data for understanding the classification accuracy. So at these 3 locations, we had seen the classification accuracy results and the relationship of the urban materials with LST. So we had seen what is the minimum and the maximum and the mean plus minus standard deviation. So you can see that the bare soil showed the highest mean LST. And if we had better spatial resolution of LST data, we could have had better results. So our next target, which I'm planning, is then the super resolution of Landsat thermal data. Obviously, because here we saw a failure in collaborating or having a relationship at the same spatial resolution. So here, okay, how do we correlate? Basically, we have brought the hyperspectral classified map into 30 meters spatial resolution first, and then did a comparison. You can never build a comparison between 8 meters and 30 meters per se. So here we have seen obviously very good results we could not expect because of the spatial resolution flaw. But again, we have seen that water showed us the lowest mean LST, and this was what we had tried to analyze at various locations. So yeah, so asphalt, then concrete, then tin. So not much of variation can be seen. But yes, we could also decipher at certain locations that wherever the spatial context or the neighboring context, wherever there was vegetation near a particular material, there the LST was lower. However, where the materials were more surrounded by those materials that absorb heat, there the temperature was higher. Even in grass patches, this particular adjacency effect can be seen. So this kind of understanding was there, LST max, and in 3 patches where one was governed by rural area, the other one was governed by a planned residential area. However, the third patch that was governed by old city area. So we have tried to analyze, and we could see that the old city area as well as the non-urban area had more LST mean temperature as compared to a planned area. So this was our finding. And yeah, so before I conclude, this is some work that I have not done. This is some work that has been done by someone. So I'm sharing it with you because it might be useful for you. People across have used indices for calculation of hyperspectral data based urban materials. So here they have used certain indices, new impervious index or road detection index, new row extraction index based on the specific bands in that wavelength region. So this is Mr. D. Pandey and KC Tiwari. I had reviewed this paper, and they have worked beautifully on extraction of different indices for extracting the built-up areas. So what I can say is that for urban areas, the hyperspectral, especially for hyperspectral data, a lot of atmospheric absorption features need to be present, which are not. So it becomes a very difficult exercise for working on hyperspectral for urban areas. Second, if you don't have a good spatial resolution, again, it is a problem because a lot of mixed spectral signatures will be there. It is as good as doing with optical hyperspectral towards ultraspectral. Maybe we are talking about hundreds of bands. There we'll be talking about thousands of bands. But how much is the classification accuracy going to be improved? Only time will tell. So I conclude my talk. I'm still 5 minutes to go, but I would conclude by a term, by a quote. If a picture is worth 1,000 words, a hyperspectral image is worth 1,000 pictures. And that is how I end my slides. So you have any questions or any queries, you can write to me, you can call me, and I'd be happy to help. So yeah, any questions?
Completely. There is a questions. Is there any questions? Uh, is there any questions?
Are they allowed to talk? I don't know, maybe.
I think, Aspaji, you can stop sharing your screen.
Yeah,
I'll
yeah.
just ask the participants if they can put their questions.
Yes, I have.
Attendees, is there any questions? Aspaji, I have one question.
Sure, please, sir.
Yeah, just wanted to know, like you have given a nice presentation on the whole importance and the urban. If a young student or a young researcher wants to
Yeah,
go ahead
I'm
and develop,
unable to hear you.
are you able to hear me now? Is it clear now? Are you able to hear Aswaji? Is there a speaker? Prashanti, are you able to hear me?
Yes, Roshan, we are able to hear you.
Yeah, I think Aswaji, are you able to hear me?
Yeah, now I
Okay.
am. Please say.
Okay. No, I just wanted to ask you, like, suppose as a young researcher or a student, if they want to take this to convert to as a product for a market or create a startup, which areas do you think in urban context they should be focusing on?
Related to hyperspectral remote sensing.
Hyperspectral remote sensing. So suppose
Yes.
I want to tomorrow focus on one area which is having a huge market and potential. How do I see that?
Yeah. So first is that in hyperspectral data, we do not
Shanti, are you able to hear her or I'm losing?
No, Roshan, we are also unable to hear you. Asfa ma'am, could you please check the internet connection? We are unable to hear you.
Of the city. So that is one area that they can or they should
Asfa
work
ma'am,
on.
your voice has been broken in between. Could you repeat
Okay.
this?
Yeah, I can. All right. I don't know. There is some connection error. What I was saying is that we do not have an inventory of urban materials in the Indian context. We do not have thermal data, thermal hyperspectral data, and that is one domain that we may like to work on. From the industry point of view, if you built an inventory of materials for any city, that is going to be a huge help for urban planners for understanding the growth of the city and the planning out the planned green spaces within the city. So a lot of research is still not done. I have not been able to do, and I would like to. One, I have told you for LST, I would like to improve the spatial resolution. The same way, you can, as young researchers, delve into building up the spectral library first for urban materials. That can be a huge contribution.
Thank you. There is one question.
Yeah.
Is there any open source available to get hyperspectral data? This is from Ms. Kanmani Kamakshi.
Yes, so the hyperspectral data from Hyperion is free of cost. However, for Everest also it is now available for the general public. You can quickly go to Everest NG website online and you can download any data within the Everest NG phase 1. It is open to any university, open to any student.
Okay. Is there any other questions? Okay, if you have any questions, I think we are also sharing the email IDs of the expert. So I think ma'am should be happy to kind of answer them or get connected with you. Ma'am, thank you. Thanks a lot. It was very informative session for us. Hope we continue to get engaged and associated with you in future workshops and projects. Thank you, ma'am. Ma'am, you're there?
Yeah, I'm there. I'm there. There's some connection issue every time popping in, but yes, I'm there.
Okay. Okay, ma'am. Thank you. Actually, I just wanted to thank you. And I think it was very informative session. Uh, what we are going to do is we'll be in touch with you. I think will also be very helpful if you can join in our future workshops and also be part of this technology innovation projects. I'm going to send you soon the details. Probably you'll
Yeah,
get it.
sure. Anytime.
Okay, ma'am. Thank you.
Thank you so much for inviting me. Thank you. Okay.
Pleasure.
Bye bye.
Thanks. Okay, I request all the attendees to have a patience. We are just going to connect our speaker. So all the attendees, participants, you can have a short break. We are getting in touch with our speaker. So the session starts at 11:15. So I request you to be around. You can keep your system on and take a short break. We'll see you around 11:15. Thank you. Good morning, Dr. Vaibhav.
You are introducing. Please.
Good morning, Dr. Vaibhav. Are you able to hear me?
Roshan, we have made him the co-organizer. He'll be rejoining back.
Okay, okay.
In a minute, he'll be back.
Well, he has joined, I think. Make a presenter also.
Yes, now he's a co-organizer.
Yeah. Dr. Vaibhav, are you able to hear us? Dr. Vaibhav, are you able to hear us?
Yeah, good Morning. I can hear you.
Yeah, hi, this is Dr. Roshan here from
Yeah.
IIT Tirupati.
Very good morning. Very good morning.
Good morning, sir. Sir, would you like to share your... Anyway, we have 5 minutes. You can share your presentation.
Yeah, I'll do that.
And if you want, you can also...
Is it visible?
Yes, sir, it's visible.
Yeah, fine.
Charge coming in. So now we have come to the second section of the day today. I take this opportunity to welcome our key speaker for this session, Dr. Vaibhav Garg, Scientist Engineer in Water Resource Department, Indian Institute of Remote Sensing. We're very happy to have you for this workshop, sir. Thank you for accepting our invitation.
Thank you so much.
So I just start the session with a small introduction about Dr. Vaibhav Garg. He has earned his doctorate degree from India's premier institute, Indian Institute of Technology, Bombay. He's presently working as a senior scientist at Indian Institute of Remote Sensing in Indian Space Research Organization since 2009. More than 12 years of academic and research experience in the field of remote sensing and GIS applications in water resource engineering. And his research interest includes mapping and monitoring surface water using geospatial tools and techniques, hydrological modeling, reservoir sedimentation studies. So I think a wide area of research interests. Wow, it's nice. And he has successfully guided a PhD student and 26 master students on critical aspects of water resource. A large number of publications in the field of application of soft computing techniques and geospatial technology in water resources, both in national and international journals and conferences. He has about a publication of 9 book chapters, and his publications have received 1,189 citations across the globe. He is also a fellow of Indian Society of Hydraulics. He is a life member of professional bodies like International Association of Hydrological Science, UK, Indian Meteorological Society, India, Indian Society of Remote Sensing, India, Indian Association of Hydrologists, India, and International Association for Water, Environment, and Energy and Society. He has been awarded the Excellence in Thesis work to the PhD student in Civil Engineering for the year 2009-2010 by IIT Bombay. He was recently awarded with Professor R.J. Grade Research Award by the Indian Society of Hydraulics. I once again invite you for our session, sir. It is really great to have you here.
Thank you so much for introducing myself to the audience. And it is in fact an opportunity for myself as well to interact with these participants of this particular workshop. So shall I start the session?
Yes, sir. You can start the session.
Yeah. So the topic given to me for today's session is hyperspectral remote sensing for water resources. So I think for last 1.5 days, you have been exposed to this technology, hyperspectral remote sensing. So you might have understood that the technology is really useful in quantifying the features and their abundance on the surface of the earth. So earlier we were able to map them. We were able to map the features present on the surface of the earth. But with the advent of this kind of technology, such as hyperspectral remote sensing, now we are able to quantify them at how much or with what quantity it is available on the surface of the earth. So I will focus today on its application in water resources studies mainly. So I will touch upon the application of hyperspectral remote sensing in understanding the snow and quantifying the snow grain size and the snow condition. And then I have some slides on the water quality, which is these two, snow and the water quality studies are the major studies being done using the hyperspectral remote sensing data. And I have some slides on the estimation of soil moisture using the hyperspectral remote sensing data. So as I told you that for last 1.5 days, you are studying this topic, hyperspectral remote sensing data. So you might have come across that earlier we used to use multispectral remote sensing data or that is optical remote sensing data, to understand the features such as the water or any other land feature or their applications in the using the remote sensing data. And this hyperspectral remote sensing is an emerging technology, as it provides in-depth means of investigating the spectral variations in the order to derive more accurate estimates of the land features. So we are able to quantify them with how much quantity it is available on the surface of the earth with the help of this kind of sensor. So today we will focus on the water quality, snow related and soil moisture retrieval studies. So you can see in this hyperspectral remote sensing data, we may mainly identify the feature or their abundance based on their spectral response. So you can see the comparison between the multispectral and the hyperspectral. So same features, how their spectral response is there in the multispectral and in the hyperspectral remote sensing data. And then we analyze these absorption dips or the pattern of the your spectral response to identify the feature and to assess the quantity or change in the particular feature present on the surface of the earth. So we analyze these kind of absorption dips, right, in the hyperspectral remote sensing data. So why we need a hyperspectral spectroscopy? So we require this technology for characterization of the objects or the target we are interested in, and then to quantify the abundance of the particular target object, and it provides the selection of sensitive bands. So you might have come across that we use band ratioing techniques to enhance the image or the optical remote sensing data for the particular feature. So we require the sensitive bands. So using the entire wavelength region from around 350 to 2500, we can identify the sensitive bands towards particular process or the feature, and then we can develop certain indices to extract that particular feature from the remote sensing data. And it can also be utilized for the classification of the targets using this kind of remote sensing data. So as I told you, we generally work with the spectral response of the particular feature in this hyperspectral remote sensing data. And if we collect the spectral response of different features present on the surface of the earth, we generally call it as a spectral library. So it is a collection of spectra of natural or any man-made feature or material present on the surface of the earth. So these libraries provide a source of reference spectra of variety of targets. So in generally these kind of libraries are available for minerals, rocks, and vegetation species. So you might have been exposed to these kind of libraries, such as John Hopkins University Laboratory. They have the spectral library with respect to these minerals, rocks, man-made features, and lunar rock samples. Similarly, the USGS Vegetation Laboratory, they have the spectral library vegetation for entire visible to shortwave wavelength region. Then JPL, the Jet Propulsion Laboratory for rocks and minerals, they have the spectral library for minerals. Again, USGS, they have spectral library for minerals and rocks. So if you see there are standard spectral libraries available for mainly for these minerals, rocks, and the vegetation. But if you see, there is no standard library available for the to study the water related aspects such as snow and the water quality. Why it is not there? Because the condition of the water or the quality of the water, it varies both spatially and temporally. So it depends upon the depth of the water, the quality of the water, right? What kind of water body it is. So it is highly dynamic in nature. So that is why we don't have any standard spectral library for these kind of features such as snow and the water. So why we need this spectral library to these are the spectral signature of the features present on the Earth. Okay, and it helps us to identify that particular feature or the target. And with the help of this spectral library, we can characterize these features based on their spectral response. And this technique has been considered as a very reliable technique to identify the feature using the remote sensing data. Spectral profiles of the elements such as rocks, minerals, snow, water should be preserved with every details. As I was mentioning, that whenever we generate this kind of spectral library, we should consider all the variations in that. Suppose we are talking about the water, fresh water, saline water, brackish water, water with different turbidity concentrations, chlorophyll concentrations. We should have water with different depths. We should have that kind of spectral library. Then only we can use that for the identification of either the quality, or in case of snow, different grain size. As you know, with the time, snow grain size changes, and as the snow grain size changes, the spectral response also changes. So our spectral library should be robust enough to have these kind of variation in that. So that is what I'm trying to focus on this particular point. So spectral features are as reliable as any other semiconductor chemical methods. So as we used to identify certain features with using this kind of chemical methods. Similarly, these kind of techniques of the similarity, spectral similarity, is also reliable, are equally reliable. So in this kind of studies, what we do from this reference spectra, we detect the particular target or the object feature. So this is generally called as known to unknown approach. So you might have come across different sensors. There are airborne sensors, hyperspectral airborne sensors. There are space-based sensors. So the few of them I have I'm sure I have kept in the slide, such as Everest. Now that Everest NG is working, then HIMAP, then HIDICE, NDICE, and there are many other airborne hyperspectral sensors available across the globe. And then these are some of the space-based sensors. Hyperion, now it is, the data is not available, but the past data it is available on the USGS Earth Explorer website. And then HISIS, India launched it in 2008, and again they have launched it, but it has been used by the military. It has been launched for the military purpose only. For public domain, the data is not available. Then Mary's is there, Chris Proba is there, and then recently the Prisma data, it is freely available. So these are some of the space-based sensors. So we have the data available with us. You might have been taught about the image processing. Whenever we have this kind of data, to carry out the radiometric corrections, then atmospheric corrections, then geometric corrections. Once all these corrections being done on your raw data, you will get the level 2 data, which we call as the reflectance data. So based on the using that reflectance data, we can extract the information or the feature of our interest. So in today's lecture, as we are focusing on water resources parameters, water related parameters. So I will show you some of the slides where the hyperspectral remote sensing data can be used in snow studies. So all of you know that snow physical parameters such as albedo, its cover, how much cover of the snow is there, what is the grain size, and the temperature. These these play the important role in the hydrological modeling. So it is important to study the snow parameters. So these parameters, if you collect in the field, you will get only the point information, and you will get the information only for the area which is accessible to you. But all of you know that the snow falls in the higher altitudes and in the rugged terrain. which is most of the area is not accessible to you. So these remote sensing data or hyperspectral remote sensing data may provide you the spatial information about these snow physical properties. So this is the typical response of the spectral response of the snow, and you can see that as the grain size changes, the spectral response of the snow changes. So snow reflects highest in the visible region and low in the shaded region, and the reflectance of this fresh snow is, you can see here, is up to 90% in the visible region and decreases with the increase in the wavelength. And if you see that the freshly fallen snow almost immediately begins to compact, changing the snowpack characteristics. So whenever snow falls, we call it as a dry snow or fine grain snow. So with the increase in the temperature, due to cohesion, the grain size changes, and as I mentioned here, and due to the compaction, the characteristics of the snowpack changes. So these some of these physical parameters of the snow can be retrieved using hyperspectral remote sensing data. So you can see here, this is the typical spectral response of the snow, fresh snow. Okay, and you can see this the spectral response of the snow. There are certain factors which affects the this particular spectral response of the snow, such as the grain size of the snow. If there is any contamination of the snow, and then what is the liquid content present in the snow, depth of the snow, and the solar zenith angle also affects the reflectance of the snow. And if there is a cloud cover present in the data, you may not get the information on the snow beneath it. So there are many factors which affect the reflectance curve of the snow. So this is how the grain size affects the reflectance of the snow. So you can see here, this is the fine grain snow spectral response curve. And then if you see as the snow grain size increases, the reflectance is decreasing. And at this particular region, we can see that there is a major change in the reflectance of the snow. So generally, this wavelength region has been used for the grain size mapping. I will show you some of the case studies which we have done for retrieving the snow grain size. So why the snow grain size is important? Because if you see, if you are a hydrologist and you have been given the task for the snow melt runoff modeling. So finer grain size snow will require less energy to melt. However, the coarser grain size snow will require more energy to melt. So if you know the grain size, it may help you in this kind of hydrological studies. If there is a shoot present on the surface of the snow, you can see that this is the pure snow reflectance curve. And then if we add the soot, you can see that how the response of the spectral response of the snow changes. You can see here, if I change the concentration of soot with different values, how the response of the snow changes. You can see here the effect of liquid water content in the snow. How the spectral response will change. You can see here, this is the response of the dry snow, and then this is the wet snow, dotted one, and then this dark line trend is for the refrozen snow. Winds during this kind of springtime, when there is a slightly temperature goes up, the snow will melt, and after immediately if there is a temperature change, that will refreeze again. So that how the response will change, it has been shown here. So if we have these kind of libraries, we can, if we can analyze the change in the spectral response of the snow, we can analyze what is the condition of snow, how much liquid content is present is there, whether the snow is contaminated or not, what is the grain size of the snow. So you can see here, Dr. H.S. Negi, he is from DGRE Chandigarh. He has done some field experiments, and using this kind of field spectroradiometer, he has generated different spectral response of the different condition of the snow. So you can see here that this is the field observed spectral response of the snow with varying moisture content. So you can see here, as the moisture condition or the liquid content of the water, liquid content of the snow changes, the spectral response curve changes. Okay, you can see here the major change in the this particular wavelength region. So if we can analyze the change in the liquid content of the snow, we know that there will be certain changes in the spectral response of the snow. So if we are getting this kind of response, we can tell that the liquid content in this particular snow is around 1.4 percent. So this is how the these spectral curves may be used in the hyperspectral remote sensing data to analyze the condition of the snow and the different physical parameters of the snow. Then, if the snow is contaminated, a study has been done by Negi et al. That they have add the soil, ash, and the coal on the surface of the snow, and then they have analyzed how the reflectance curve of the snow will change. So in the surface, they have a particular size of contamination. They have in a particular in the known quantity in the particular pattern. They have mixed that particular contaminant such as soil, ash, and coal, and then they have analyzed the response of the snow. So you can see here, when I add the soil with known quantity on the surface of the snow, so how the reflectance curve will change. So you can see here, this is the response of the fresh snow. There is no contamination. When I add the soil with known quantity, you can see how the response changes. We have seen that because the soil is present, so if you have noticed that the soil has low reflectance in this particular region, so that is why the reflectance of the snow has reduced due to the presence of the soil. Similarly, if we add the ash in the snow, you can see here, this is the response of the fresh snow. And if I add the ash in the known quantity, how the reflectance will change. Similarly, if I add the coal, how the reflectance will change. Now, why we need to study these contamination? Because you will not in the lower altitudes, okay, where the snow line starts, you won't find there will be contamination of the soil and the snow. I'll show you some of the photographs also. So you should know the condition, and with the help of this kind of spectral library, you can analyze the condition of the snow present in the particular region. Ash, from where the ash will come into the snow. So if you have the forest fire because of the blowing wind, it will spread over the snow, and it will change the spectral response of the snow. So we should know these kind of effects of the contamination on the reflectance of the snow. So suppose somebody have been asked you that the forest fire has took place, and how much is the effect of this kind of forest fire on the snow. So that if you have this kind of spectral library, you can analyze the your response from the hyperspectral remote sensing data, and can tell that yes, the snow is contaminated with this much of the quantity. That was the these experiments were on this. They have mixed these contaminants on the surface of the snow. Now, in the second experiment, what they have done, they have in the volume, in the entire ice or the snow pack, they have mixed the contaminants, and then again in the dark room, they have studied the spectral response of the snow with this kind of mixing, volume mixing. So you can see if I add the soot in the known quantity, how the spectral response of this the snow will change. If I add the soil, how the spectral response of the snow will change. So these libraries help us to identify the condition of snow if we don't have the access to the particular location of the snow fed region. So what I was telling you, that this is the snow contaminated with the soil. So you can see here. So in that conditions, you will get the lower reflectance as compared to the as we have for the fresh snow. So this is the snow, 100% snow reflectance, and if there is 25% soil and 75% snow, this is the response. 50% snow and 50% soil, this is the response. So now it is taking the response of the soil. So you can see that this is the reflectance of the dry soil, and this is the snow. So because of the mixing, we are getting this kind of spectral response of the from the snow surface. Similarly, the aspect or the slope of your terrain, because the snow falls in the higher altitudes, we have different slopes and aspects in this region. So the aspect and the slope also play a role in the reflectance of the snow. So this kind of arrangement has been made with this. We can tilt this particular platform in a particular angle, and we can see with the help of this kind of field spectroradiometer how the reflectance changes with the aspect and the slope. So this is the spectral response of the snow um, in different aspect in different slope angles and the aspect. So this is the north aspect, east aspect, south aspect, and the west aspect. So you can see here that the snow the spectral response changes with the slope as well in different aspects, right? So if you see, we have more solar insolation or in the south aspect, we have more reflectance as compared to the north aspect. So these are also important in hydrological studies, because the melting will be more in the southern aspect, because the region is exposed to the sun, whereas the in the northern aspect, the snow will retain for longer time period, and melting will be less in the northern aspect. So that is why the study of the aspect on the snow reflectance is important. So in the higher altitudes, you won't find the entire land is covered with the snow. It will be mixed with vegetation. So how vegetation will affect the reflectance of the snow? You can see here what they have done. They have mixed the snow with some of the vegetated material, and then they have analyzed the change in the spectral response. So you can see here, this is the response of the vegetation, the spectral response of the vegetation, and this is the snow. So because of the mixing of vegetation and the snow, you can see, you will find this kind of spectral response. So if you have these kind of libraries, you can analyze, you can generate your spectral library, and you can tell what kind of snow is present in the particular location with the help of hyperspectral remote sensing data. So I will touch upon some of these case studies what we have done at IRS for snow grain size mapping. So in this study, what we have done, our objective was to identify the snow grain size. So for that, first we have to know the snow cover area. For that, we have first used the NDSI approach and the classification technique on the hyperspectral remote sensing data, and then on we have marked the other land use classes. Only we have kept the snow cover area, and then we have applied two approaches for the snow grain size mapping. One is classification technique, another is the grain size index approach. So for this study, we have chosen the Hyperion data of the Himachal region. So this is the Hyperion data of in this study. What we have done, we have taken two time images. One is March and another is July of same year 2005. So what we have considered that in the March image, you will have more, as we were not having any observations. So what we have considered in the March, we will have mostly the fine grained snow because of the recent snowfall in the region. Whereas in the July image, what we have considered, whatever snow is there, it will be coarse grain snow because of the increase in the temperature. They might have changed their grain size from fine to the coarser. For this study, we have used the NV software where we can analyze the hyperspectral remote sensing data. So this was our methodology. We have taken the Hyperion data, then we have done the bad bands, bad columns removal, then we have done the atmospheric correction and topographic correction, and then on the reflectance image, we have directly applied the grain size index, and then in another approach, we what we have considered that in the March image, whatever snow is there, it will be coarse grain, and in the March image it is fine grain, and in the July image it is coarse grain snow. So we have extracted some of the spectra, and then we have used the spectral angle mapper approach for mapping of the grain size. So in the spectral angle mapper approach, what we do, we compare the image spectra and the field spectra, and the angle between the image spectra and the field spectra, wherever the angle between the two is minimum, we assign that this image spectra, the field spectra is matching with the image spectra, and the field, and during the field we know the condition of the snow or the water, so we can tell that this is the condition at particular image pixel. So in that way the SAM classification has been done. So this is how the atmospheric correction has been done in the NV. Then the topographic corrections has been done, and then these are the both the time images. The July image, Hyperion image of the July, and this is the Hyperion image of the March 2005. So these were the spectra what we have extracted from the image to generate the spectral library from the July image and the March image, as we were not having the observed data. So then we have generated the snow cover map of both the time periods. This is the July and this is March, and then we have applied for extracting the snow pixels, we have applied the normalized difference snow index approach, where we take the green band and the swirl band to separate out the snow pixels. And on the snow pixels, we have applied this grain size index approach, which has been developed by the Nagy et al. In 2010, where they have used this 590 nanometer and the 1050 nanometer wavelength regions to map the grain size. As we have seen earlier in these graphs, that this particular region is sensitive to the grain size. That is why they have taken the 1050 nanometer region of the wavelength for grain size mapping. So this is the snow cover map using two different techniques, NDSI and the SAM approach. And this is for the July image, the snow cover area using NDSI approach and the SAM approach. So both of them are equally performed well. And then we have applied the both for snow grain mapping, we have applied the grain size index approach developed by the Nagy et al. And SAM classification approach. And you can see these are results of the snow grain size mapping. So here in this image, the green pixels represent the finer grain snow, and the red pixels represents the coarser grain snow. So this is the condition in the July. As I told you that during the July we will have majorly the coarser grain snow. So in that way we can map the grain size of the snow. And this is the grain size map of the March data, where we have considered that the snow is finer, mostly the finer in the in size. So you can see that green pixels are more in this March image, because in the March image more fine grained snow is available. So this is how the hyperspectral data may be used for either grain size mapping. Similarly, you can use this technique for identifying the liquid water content in the snow, or you can use the this data for the different physical parameters, as we have discussed earlier. So this is how this kind of outputs you can generate, that where in which region what kind of snow grain size is available. Then similar studies we have done using the airborne average NG data. So this is one of the strip of the Everest NG. It is near to Patsio Glacier in the Himachal Pradesh region. So in this study, what we have done, we have selected this horn. You can see here, this is the top of the this particular mountain, and this is the surrounding. So in this study, again, we have used this grain size index approach for the grain size mapping. So you can see here, as this image is of February 17, 2016, we have more of the finer grain size. Now you can see here there are some pixels where the coarser grain size is also there. I like to draw your attention here that if I take this is the digital elevation model of the same region, and this is the aspect map. So you can see here this particular region is in it is in the so this is in the southern aspect. That is why the grain size was coarser in nature. So you can see here on this particular horn, what we have done, we have extracted the response of the snow in different elevation zones. So we have divided this region into number of elevation zones from 1 to 16. From the range of the elevation is from 3,500 to 5,700. At every 500 meter, the elevation zones have been drawn, and each zone we have selected some of the points in each aspect. This is with respect to particular elevation zone, how the response of the snow is changing. So this is for these pixels in a particular aspect. This is mainly the south aspect. So you can see here at each elevation zone how the spectral response is there. You can see here as we go down in the elevation, you can see that the response or spectral response of the snow is changing. Why there is a change in the spectral response of the snow with the elevation? It has been considered that in the higher altitudes you will have more fine grained snow as compared to the lower elevations, because the temperature at the higher altitude is low. So the fresh fallen snow, it will not start melting because of the temperature, lower temperature. Whereas in the lower altitudes, because of the slightly higher temperature as compared to the top of the mountain, they will immediately start melting, and their grain size will change from finer to either medium or the coarser. So because of that, the response of the snow is changing with the elevation. Similarly, what we have done, we have extracted the spectral response of this horn in different aspects. So you can see here, these are the points from where we have extracted the response of the snow. So these colors represent the different aspects, slope aspects. Okay, so these are the aspects, and these are the response. So as the Nagy et al, they have extracted the response or taken the response of the snow in different elevation zones, in the different slope and different aspects. Similar results we have found in the satellite or the image of the satellite, sorry, airborne hyperspectral remote sensing data. That in the southern aspect we have more response as the higher reflectance in the snow, and as the in the northern aspects we have less reflectance from the snow. Then these are all what we have done on the snow studies. Now I will touch upon some of the slides on the water quality studies. So all of you know that water quality is a measure of stability of water for specific use based on its physical, chemical, and biological properties. So whenever I talk about the water quality, I start with this slide. So you can see here, this is one of the Osbach Lake in the USA, and this is the Landsat image, not hyperspectral, multispectral only. But you can see that the tonal variation in the water. So this is water. All of can understand that this is water, and you can see that there is a sudden change in the tone of the water in at this particular location. So if you see, there is a one channel. It is coming and joining the water body somewhere here. So you can see here this channel is bringing sediments along with it, and it is merging with the water of this particular lake. Okay, so that is why you can see the change in the spectral response. With the help of remote sensing, we can generate this kind of quantitative maps that how much concentration of sediment is there in particular section of the water. So there is a huge opportunity of mapping this kind of water quality parameters using remote sensing data. So why we need to study the water? Because as you understand that our earth, it is composed of around 70% of water, and out of that that much water available on the surface earth, 97% water is stored as as slime water in the oceans, and only the fresh water available is 3%. And out of this 3%, if you see, most of the water is stored in the groundwater as a groundwater storage, or as ice caps and glacier in the higher altitudes. So on the surface, we left with the very minimum amount of fresh water. And again, the climate change has impacted the ability of the water and the quality of the water. So that is why it is important to study the water available on the surface of the earth. So this is how the energy or light will interact with the water or any feature present on the earth. So but if you see what happens in the water, whenever the energy incident upon it, some of the energy will get reflected back to the sensor, some may get absorbed, most of the energy will get absorbed, and some may get transmitted because of the constituents present in the water. So what are so this is the total energy. And then if you see in different wavelength region, if you see the water, this is the absorption attenuation. You can see here the attenuation is higher in the NIR band and beyond the NIR, and you can see here it is higher in the blue ultraviolet region. Similarly, if you see the scattering, if you see the scattering is higher in the blue region, and it goes on decreasing with the wavelength. So that is why the water appears blue to our eyes, because it has higher scattering in the blue region. So based on this, these are the spectral curves of the common features present on the surface of the earth. So you can see here, this is the dry soil, this is vegetation, and this is the spectral response of the water. So you can see each and every feature on the present on the surface of the earth, they have different spectral response. And with the help of this spectral response, we identify these kind of features present on the surface of the earth. So this is how the water will appear in the remote sensing data. So you can see the spatial resolution, how this play important role in mapping of the water body. So this is the 500-meter MODIS data. This is 56-meter AWIFS data. This is 30-meter Landsat data. This is 10-meter Sentinel-2 data. So you can see that we can map the water body with higher accuracy using the higher spatial resolution data. So we can map the water body easily using the remote sensing data, any optical remote sensing data. But we don't know the quality of the water. So water can be mapped, but we don't know the quality of the water. So this spectral response, what I have shown you of the water, it is been affected by many of the factors, such as time of the year, sun elevation angle, the constants present in the atmosphere, the roughness of the water, and if something is floating over the water, and the depth of the water, and the turbidity of the water. So there are many factors which affect the spectral response of the water. So if we analyze the changes in these factors, so this is how the energy which is coming from the sun, what will happen? Some of the energy will reflect back from the atmospheric constituents. So some energy will get reflected from the surface of the water. Some may get reflected back to the sensor if there is any constant present in the water. And if it is a shallow water, you may get some radiance from the bottom as well. So what our sensor is receiving, our sensor is receiving the sum of all of them. The path radiance, the surface radiance, volumetric radiance, and the radiance from the bottom. See if the constituents present in the water changes, this volumetric radiance will change. And if it is a deep water, then you may not get this reflectance from the bottom. So if we analyze the change in the composition of water, and we simultaneously, if we analyze the change in the reflectance, what our sensor has received, we can develop some relationship and we can do the water quality mapping using remote sensing data. So this is one of the this is the principle of water quality mapping using remote sensing data. So same thing I have mentioned here, that this is the sum of path radiance, surface radiance, volumetric radiance, and the radiance from the bottom, whatever our sensor is receiving. Any change in the volumetric radiance due to the quality of the water, if we know in the field, we can develop certain relationship. Again, that the depth of the water, as we have talked, that because of the if it is a shallow water, you may get some reflectance and it may hamper your analysis. So a study has been done that the water penetrates highest in the particular region, that is blue region. So this is what it has been done on the Landsat 1 data, that in particular wavelength region, it penetrates up to 10 meter. In this particular region, it penetrates up to 3. In the red region, it is up to 0.1, and in the sway region, it is NIR region, it is up to 10 centimeter. So same thing is been shown here. You will get more reflectance from the surface. As you go down up to 20 meter, you may get some energy back to the sensor in the blue region. As the region, as the wavelength increases, we will not get the radiance from the bottom. So same I have depicted here in this figure. So this is the green band. You can see here. Yeah, this is the one of the coastal region, and you can see here you are getting some reflectance from the bottom. This is red region. You can see that now the it has reduced, and in the NIR region you can see here you can easily demarcate the land and the water boundary very nicely. You can see here. So this is because in this particular region we get the bottom reflectance as well. So we have to be very careful while doing any analysis using remote sensing data on water. We should know the depth of the water as well. So similarly, we have shown the example of Chilika Lake. So you can see here in this region, we are getting more reflectance from the bottom. So there are different water quality parameters, physical, chemical, and biological. So physical includes temperature, transparency, turbidity, total suspended solids, color, odor, taste, and chemical involves all these kind of things: sodium, potassium, calcium, their concentration in the water. And then biological parameters such as the concentration of phytoplanktons or algal bloom or any other microorganisms or dissolved organic matters. So if you see, there are number of water quality parameters, but using remote sensing, it has certain limitation that only the parameters those affects its optical property, those only can be mapped using remote sensing data. If you see the literature, you will find the literature mostly these kind of parameters: turbidity, total suspended solids, or the chlorophyll concentration, or the dissolved organic matter. These have been addressed using the remote sensing data, because all these parameters affect the optical property of the water. And all of you know that these kind of parameters, they get dissolved with the water and they do not change the color of the water. So that is why it is difficult to retrieve the chemical water quality parameters using remote sensing data. So these are certain optical properties of the water: inherent optical properties, IOP, the properties which depend only upon the medium and are independent of the ambient light field within the medium. Whereas apparent optical properties, those properties that depend both on medium and the directional structure of the ambient light. So if any of these optical properties of the water gets affected because of the quality, these can be retrieved using the remote sensing data. So chlorophyll is the one of the parameter which has been or the turbidity or the suspended sediments have been addressed using the remote sensing data. So on the surface of the earth, we won't find the clear water or clean water. Whatever water we have on the surface of the earth, it will either this is the whatever reflectance or the radiance we receive at the sensor, it is a function of the water, clear water, and the suspended matter present in the water. If there is any chlorophyll concentration is there, and then the dissolved organic matter. So it is a function of all based on their concentration. If the concentration of any of these changes, your reflectance or your radiance received at the sensor will change. So if we analyze these parameters on the ground, we can analyze the change in the radiance. We can develop certain models to map these kind of parameters using remote sensing data. So similarly, so these parameters on the especially the turbidity, it has been measured through this kind of simple instrument called as Shashi disk. See, we lower down this particular plate, which is alternately painted as black and white. We lower down this instrument with the help of this kind of weights in the water body, and we measure up to what depth this plate is visible to our eyes. So that means that up to that depth, what water is visible, or the energy is reaching up to that point, particular depth of the water. And the turbidity, it has been measured in the field with the help of the turbidity meters or transmission meters. So what we do, we have different standard solutions of known turbidity, and we calibrate our instrument, and then what we do, we collect the sample from the field, and we put that sensor in these kind of instruments, and we pass the light through the sample. If water is clear, the light will pass through. If water is turbid, what will happen? It will scatter in all different directions, and then we analyze the scattering in the particular angle, and then we estimate the turbidity in the field. So if you see, even these kind of samplers are available. We collect the samples, and then we analyze these samples in the laboratory for the concentration of the sediments present in the water. So if you see these kind of field sampling, it is very difficult and time taking, and we will get information only for the particular point or particular location. However, this quality of the water changes spatially and temporally. So similarly, we can collect these kind of we can generate the spectral library of the water. Add that in the water, how the response of the water is changing, you can see here. So if you have the hyperspectral remote sensing data, because multispectral remote sensing data, you will not get this kind of entire spectral response. If you have the hyperspectral remote sensing data, and the in the image you are getting this kind of response, you can tell that in this particular location, the silt is present with around 250 milligram per liter. The concentration of silt in this particular location of the water is around 250 milligram per liter. So this is how the hyperspectral remote sensing data may be used in the water quality studies. Similarly, as I told you, in the water, some locations you will have also you have the planktons may be present. Either it is phytoplanktons, zooplanktons, bacteria planktons, or algae, fungi. So these phytoplanktons, they have this photosynthetically active pigment chlorophyll. So because of the chlorophyll, the response of the water will change. So this is the spectral response of the clear water, and this is the response of the algae laden water. So you can see here, because of the presence of the chlorophyll in the algae, there is a sudden absorption of the energy in this particular region, and then there will be high reflectance in this region, and again there is a absorption in the red region, and then this particular region, this region is called as red edge. So so this is how these are the experiments done in the lab. They have added in the algae laden water, they have added the sediments, and then they have analyzed the response of the water. So you can see here. So generally, this chlorophyll has been estimated using the ocean color monitor kind of sensors using this band ration technique. So as we have seen that there is a sudden absorption in the blue region. So mainly the blue region has been used with other wavelength regions. The band ration technique has been used for the chlorophyll concentration estimation. So I'll show you some of the case studies. First, I will focus on the methods. So what kind of methods have been used for water quality mapping? So these are the simple empirical approach, where we have, if we know the concentration of the particular water quality parameter at particular location, and if we have the remote sensing data of particular water body, if we develop a relationship between
Thank you. So I think there are a few questions. Is there any questions from the attendees? Hello. Is there any questions? Dr. Vaibhav, I have one question. Dr. Vaibhav, are you able to hear me?
Looks like he's reconnecting, Roshan.
Okay, okay. Meanwhile, audience, the participants, if you have any questions, can you post it in question and answer? Okay, I can see. One question is, can you please share the PPT? What we're going to do is we're going to collect all the presentations from the experts, and together we'll post it in the drive and will be shared. Dr. Vaibhav? Dr. Vaibhav, are you able to connect? Oh, he's not there. We'll just hold on for a couple of 5 minutes. The speaker is trying to get connected. Okay, I think the expert Dr. Vaibhav is not able to connect back. What I'm going to do is I'm going to collect all the questions what you have put up in the Q&A, and we'll close the session now. I request you, all of you, to come back by 1:30 a.m., have lunch, and after post lunch, we'll start from 1:45. We have a session. There are two sessions after the lunch, and then there's a closing validatory session. So please join us. The meeting will be open. The link will be open, so you can leave your systems connected. Please come back at 1:30 for the next session. Thank you.